Okay, so now let's do some examples applying the method of solution. So we start with the RL circuit equation. So we have L dy dt R times the current and equal to the voltage. Okay, so first we convert it to a standard form. And now we follow the steps from the previous video. So first we multiply by the integrating factor. So mu of x. So we get mu of t. And then mu over L sine gamma t. Right. So so you don't have to do this every time. Hopefully you know by now that this is that mu prime has to equal mu times RL. So you always get mu of t is the integral of this coefficient pt. And so you can directly write what mu is. You don't have to do this every time. So here we have R over L. So R over L T. Okay. Right. So the next step was what? We had d dt of mu times y equal to mu sine gamma t over L. And then we integrate. So y of t is equal to 1 over mu t, and then integral of mu s sine gamma s over constant L. Okay. And then we plug in our mu. Sorry, plus a constant. Always remember the constant. Okay, so that's it. That is the solution to the RL circuit. Okay, but we can simplify this solution. So let's try that. So simplify. Okay. So of course the toughest part is evaluating that integral. So let me write you a general formula. So in general, from integration by parts, you have the following. So let me do this. So e to the b s. So e to the bx times the sine of ax dx is always equal to the following. So a squared plus b squared and sine of ax times b minus a of cosine of ax in this entire thing times a to the bx. Okay. So let's apply this to our case. So this integral will be equal to the following. So we have R over L, ratio of resistance over inductance. Times the phase gamma, cosine gamma, and then gamma square over RL plus R over L square. And of course times our bx. So R over L t. All right. So now let's write down our solution. So y of t is equal to the following. So let me do a shorthand for this gt. So we had, let me go back. So we evaluated this guy. Let me write it. E to the minus r over L t integral of gt plus the constant. Okay. So actually you can further simplify it. So you have this guy which goes to 0 as t goes to plus infinity plus this ratio. Okay, so this guy goes to 0, and this guy is periodic. Let's go to our MATLAB simulation. So over here. So this is our equation. I gave you the code in discussions, so you can run it yourself. So this is the equation here, and let's run it. So we see that first you start from this exponential guy, which quickly decays down. So this is the exponential, and then we have the periodic part. Okay. So let me run it one more time. And the arrows here represent the direction of the derivative. This one we will talk about it later. This is called the direction field. And the solution has to follow the arrows. But more on that later. Okay. All right, so we found it. This equation governs the um, RL circuit in time. And it says that you start from 0 and then the current becomes periodic. Okay. Let's do one more example. So consider the following homogeneous ODE. Now, first, always you bring it into standard form. So dy dx. And so right away you see that there's something happening at 1. So our solutions only make sense for x bigger than 1. So 1 to infinity, and x smaller than 1, minus infinity to 1. But at 1, we do not have a solution. No solution. Okay, so let's start again. So this is, here is p of x. So again, we multiply by mu, the integrating factor. And we have mu dy dx. Let me write it as plus mu x and then the coefficient. And here we have the forcing. So, okay, as usual, mu would be the integral, the exponential of the integral of p of x dx. And this is just the ratio. So you can quickly find this to be just x minus 1. Okay, this integral. Okay. So we found mu, and as usual, we have our product rule. Product rule step. So what is it? Mu y prime is equal to mu of x 1x minus 1 squared, forcing. We integrate it. And you can see that this is just the derivative of this exponential. So here we use the chain rule. If you have questions, let me know in discussion board or in office hours. So we do this, and we get minus 1 over x minus 1 plus, of course, the constant. Okay, so we found our y. Y of x is equal to 1 over mu of x. And mu of x was this term. So we're left with minus 1 plus constant e to the minus x minus 1. Okay, so that's the solution. Let me make a comment. So right away, you see that there's something funny happening at x equal 1. Okay, so we have the following bifurcation, the following split. Let me write it one more time. 1 minus x. If x is less than 1, then as x goes to 1, the 1 minus x becomes 0. So we get infinity. And I will graph this in MATLAB as well. But if x is bigger than 1, then as x goes to 1 from the right, we get minus infinity here, so we get 0. Let me draw them just to give you some intuition, and then we will do the MATLAB. So this is x. This is the blow up point, and this is y. If x is less than 1, then our solution will go up like this. And if we're over here, our solution will go down like this. Okay. So now let's run the simulation. So here x is less than 1, and it goes up, 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 and it blows up. And here x is bigger than 1, so it goes up for a little while, and then it will come down and become 0. Okay, let me run it one more time. So solution goes up to infinity when x is less than 1, and when x is bigger than 1, if you start the solution from here, time 2, you will go to 0. But if you start at some time before 1, you will go to infinity. Okay, so that's it. Let me make my smiley face. We will do more examples, but they will be optional. So, thank you.